for multitask RL, some methods for meta RL, which is closely related to multitask RL. And then finally, we'll start touching on offline RL or learning from prior data sources. Okay. Hmm. Okay. Hmm. Okay, that works. Okay, good. So, multitask RL. We're going from solving a single MDP to solving a distribution of our MDP, right? So we want to solve not just a single MDP, maximize the expected sum of rewards. Instead, we're going to start solving a distribution over MDPs. So we're going to have a distribution over transition dynamics and rewards. We're going to say we want to learn how to maximize the reward across those distribution of problems, right? And so the difference here was that here you could get a single policy. You don't really care about generalization. You really care about like optimization, care about maximizing goal. And the goal here is you care about generalization to the k plus 1th problem. You don't care about just maximizing reward in the training set. It's really about generalization. So the assumption we're going to make is that states and actions are the same. So we can run a single policy across everything, right? So often you have states be images and actions, you're going to keep the same robot. But you could also have variants of this where the actions and states are different. But for simplicity, we're going to say states and actions are the same. Transition dynamics and rewards can be different, right? And specifically, we're going to assume this meta MDP. So it's an MDP which looks like a standard MDP, but it has an additional omega I variable. Which omega I is something that denotes what task you're trying to solve, right? So it's trying to say something like a language instruction or a goal image or something that denotes which problem you're in, because otherwise you don't know how to solve your problem. So you're going to assume access to this omega I. It could be like a task ID, also something like a one-hot vector. But your transition dynamics and your reward are going to depend on this omega I. So given this kind of reformulation, we're just going to augment our state with omega I. We're going to have our transition dynamics depend on omega I, and we're going to have a reward function depend on omega I. Right? And so the point here is that really we didn't change that much. Like assume that omega I was something like a task ID or something like a language instruction. All this is saying is that add that into your state. And so you run all your plain old RL methods, you're just going to add in something that describes the task into the state, right? And so we're essentially going to use all of our single task machinery, everything we did in this class, and we're going to apply it to multitask RL with just an expanded state. And the state, this part will evolve according to the dynamics, this part will remain constant across time. So all we're going to do is add omega into the state and run RL. For a new problem, take whatever omega you have, stick it into your policy, run your model, right? So let's say you had a policy that took in a language instruction. You're going to try and learn a policy over k different language instructions, and then stick in a new language instruction and ask the policy to do the task, right? That's the kind of setup we're doing. All right, so the paradigm we're gonna consider is something like this. You sample data across all the tasks, right? Using the same policy, but with different task IDs or with different omega Is. Then you're going to collect all of your data into a buffer, but remember that your data is labeled with S, A, S prime, and your task ID or your omega I parameter or whatever identifier. And then you're going to run actor and critic updates, same as usual, but you're going to like, let's call them taus instead of omegas, but you're just going to add in tau into your critic, into your Q function, and you're going to add in tau into your actor, right? So tau is going to go into your actor. So you have a task condition policy, you're going to have task condition critic. Right? So everything remains the same. You've just added a task descriptor to the actor and the critic. Yeah. And if you do this, you see that it does extremely poorly, right? So you see that multitask RL does really badly. It's sitting at like 20%. Whereas if you look at single task RL, shown in pink, I think, it's getting up to 100% success rate. So it's not just like, I would actually expect this thing to be faster than this thing because you're sharing data across lots of tasks. But this thing is not only slower, it just like is asymptotically a lot worse, right? So the simplest strategy of just taking single task RL and doing it on an expanded state space doesn't work. Right? It doesn't do it well.
Question. In your indeed experiment, was the policy that is being trained for the multitask RL the same size in like the complexity as like the single task one, or was it like
Yeah.
and
Yeah, so I think we use the same size here. We also tried expanding the size, and expanding the size doesn't actually make the bottom line better. So yes, this thing has to learn 10 policies, this only has to learn one, but even if you make this 10 times bigger, it doesn't learn better. And the other way around too. So just to make sure I give you context, this is trained on this domain called MetaWorld, which is like 10 robotic manipulation tasks. And we're not even testing on the 11th task. You're just testing on, can it learn the 10 training tasks? And then you start seeing that it like cannot even learn the 10 training tasks. And so often when you, in your applications, when you try doing multitask RL, you'll find that it often is much harder to train than single task RL. This is also true in imitation learning to an extent, but it's worse in RL. I'll talk about why in a second. Okay, so the problem we're going to try and solve is this asymptotic or a suboptimality, if you will, right? So there's like a gap between this yellow line and the pink line that we want it to be. So ideally what we want is this thing is actually something that learns quicker and reaches the same or similar asymptotic optimality. Right? Okay. Make sense? So that's the problem we're going to solve in multitask RL. There's a much bigger field. I'm just going to talk about this particular problem. Okay, so the issue is that if you try and train policies across all of like a bunch of different problems, what starts happening is that different tasks start interfering with each other, right? So if you have, let's say, two different tasks that take you in two different directions, let's say you had like pickup, and pickup is telling your policy parameters to go this way, and pushing is telling your policy parameters to go this way. This thing starts to hamper the performance of this guy, and this thing starts to hamper the performance of this guy, right? And so in single task RL, this is not the case, or it's kind of the case you can have it between different states, but it's much less of a problem. In multitask RL, often you'll see that one task may be at the expense of another task. And so this like you start to have negative interference between problems that are different, right? And so the primary cause that we think, I wouldn't say there's 100% identified, but that we think is the issue with multitask RL is that when you have multiple tasks whose objectives might be conflicting with each other, that leads to like the optimization landscape not reaching an optimum with stochastic gradients in practice, right? So pictorially, it looks something like this. You'll have some task Gj, you'll have another task Gi. You can see that moving in Gi and it goes in the opposite direction to Gj, right? And so you'll see that these two things are conflicting. And when this is paired with this online data collection procedure, it does really, really poorly, right?
Because you fall into a local.
Yeah. So you're always in some sort of a local minimum, but it's particularly bad because what's happening is so in some sense, even when you multitask supervised learning, you'll have this problem. But what's particularly bad about multitask RL is that you're putting data collection in the loop. So imagine that you had multitask supervised learning, right? So you had one task taking you this way, one task taking you this way, or maybe one task taking you this way, another task taking you this way. You'll still have some conflicts, but your data set is static. Right? So you're just continuing to do updates on the same data set. In multitask RL, what happens is your data set is being collected by your policies. And so if you have one thing conflicting another thing, and let's say like one of them, you move more in the direction of one of the tasks than the other, then the data for the other task starts to get worse and worse and worse. And then you never recover, right? So it's like local optimum, which gets worse with online data collection. Whereas in supervised learning, their data is static. And so I think that's what makes it different. You have a question, sir? Okay, so the main points I want to make here are that conflicting gradients can be a problem, but they're a problem in almost any multitask setting, but they're particularly problematic when you have online data collection, right? And so when you're like collecting data on the fly, and you have many tasks, you have this winner take all type phenomenon. So you have this is a really nice paper called ray interference. You all should read it. But basically they try to analyze this interference phenomenon in deep RL, and they show that deep RL has a lot of these like plateaus when you have multitask behavior. And they see that the like behavior looks like that is the optimum top right. And instead of going straight to the optimum like you'd expect in supervised learning, they find that when you do multitask RL, it has this like really meandering behavior, and sometimes it like gets stuck until noise gets you out of it. And so they talk about this winner takes all phenomenon, where if you have like two tasks, and let's say one of them you're going more in the direction of one, the data collection gets worse than the other, and then you never recover on the other task. So you'll succeed at one but not the other. Thank you.
The different tasks simultaneously rather than like going like from one task to the other, like 1 hour.
Yeah. Because so the setting that we usually will do is we'll sample but you'll sample like a batch of tasks, right? So like in step one, you'll sample data across many tasks at once, and then you like optimize the batch across all of them. The problem with doing them one at a time is that you'll start to forget the next one when you've done the first one. So the hope here is that because you're training them all at once, things from one task can help another task. But that doesn't happen here yet. Yeah. But if you do things that are more sequential, it starts to look more like continual learning. Continual learning has this problem of catastrophic forgetting, where you'll forget on the K+1 at the yeah. So go take a look at this paper, but this is a nice pictorial illustration of if you're in supervised learning, you see you'll go to the optimum quickly. If you're in tabular RL, which is like not with deep function approximation, where these gradients don't really interfere because it's tabular, you see you'll again go to the like there's relatively less hit rate, right? And as a result, there's also less plateaus. But if you look at deep RL, you'll see that it has like tons of these plateaus where it gets stuck for a while, even in a simple 2D problem. And you'll see that like the landscape of the parameters, it kind of like tends to have this winner take all phenomenon where one thing wins and not the other. Right? And so often the reason this performance is like sitting at whatever 20% is because like 3 of the tasks are optimal and like 7 of them are just 0. Right. And so at least what we found that happens pretty consistently across benchmarks.
Is this graph showing one task performance or like average across all?
It's average across.
Is there also a graph that shows like, hey, doing really well on some tasks, like really poor?
I don't remember. But you should check. This is from this paper, EC grad. That look at my Google Scholar from a few years ago. Okay, so the problem we're looking at is that it's not just conflicting gradients, because you see that even in supervised learning, there was conflicting gradients. Right? It's the combination of conflicting gradients and exploration. So when you're collecting data online and you have conflicting gradients, that's the problem. Right? So almost all multitask problems have conflicting gradients. It's just that when it pairs with exploration, you're in trouble. Yeah. Okay, so we want to fix this problem of conflicting gradients and dealing with exploration. How might we fix it? What are some ideas? So the two issues are we have conflicting gradients across tasks and you're doing online data. Right? How can you fix it?
Offline.
Offline. Great. So we can try and remove exploration. We still have to explore somehow, but we can try and remove exploration. What's the other solution?
Maybe find with MBR approaches, like you only have to learn cost, maybe dynamics as well, but you effectively break it down so it's
nice because you're like doing test time optimization per task, so you never have to optimize for multiple tasks. The challenge is that you as your tasks get more complicated, your test time compute gets more complicated, right? And so then it becomes like harder and harder to achieve the same performance. That's a good idea. Other thoughts? So our problem is conflicting gradients and exploration. We said we're going to get rid of exploration, and we'll talk about how. What is the other thing we can do?
There's maybe there's a way around the conflicting variance, like, I think it was like some work that we discussed where you kind of always take an orthogonal, I forget the name, it's like conjugate or something.
Yeah, that's right. So you don't modify the gradient, so they're non-conflicting, right? So, simple way to think about it is exploration and conflicting gradients is bad. One solution is get rid of exploration, the other solution is get rid of conflicting gradients. So you're going to an orthogonal projection like Sid is talking about. So those are going to be our two solutions. Multitask RL is bad because of this combination. We're going to either try and get rid of exploration, and so we're going to try and make it as offline as possible, or we're going to try and get rid of conflicting gradients. Right? So there are going to be two different methods we discuss. Questions? Your thought?
But then, how can you don't have all of your theoretical guarantees of gradient descent?
You lose. We'll talk about that in a second. You lose like some convergence, right? But you'll still converge. Okay, so a simple observation is that if you do multitask supervised learning, it's stable. Multitask RL is unstable because of this combination of exploration and conflicting gradients, right? And so the insight here is that single task RL is easier and multitask RL is harder, right? And so multitask RL with a combination of multitask learning and online data collection is hard. Single task RL is easier and multitask supervised learning is easy. And so what we're going to try and do is we're going to try and convert a multitask RL problem, right? We're trying to convert a multitask RL problem into a combination of single task RL and multitask supervised learning. Okay. So what I mean is that I'm going to try and solve exploration problem single task, and then I'm going to try and get it to a generalist policy by doing supervised learning. So that the only part that's going to be multitask is a supervised learning step, and the RL part is going to be single task. And so, so the idea here is you want to convert a multitask RL problem into a combination of single task RL and multitask supervised learning. Okay, so there's like a divide and conquer approach to multitask RL. So essentially it's saying that imagine you had a bunch of different tasks or even a bunch of different initial conditions. What you're going to try and do is you're going to try and learn experts for different initial conditions with single task RL, and then distill them into a single expert with multitask supervised learning. Okay? And so this is a nice graphic I stole from some folks at DeepMind. But basically they say, you have 4 different types of environments. You're going to learn a single task policy on each of them. And then you're going to try, and so you're solving a single task RL problem, and then you're trying to distill this back into a single multitask policy with supervised learning. Okay? So you're doing single task RL and then multitask supervised learning. We'll formalize this in a second, but the thought is that we never have to face the pains of multitask RL because you're only doing multitask supervised learning. And each of the single task RLs is like you have many different experts, you distill them, many different experts, you distill them, many different experts, you distill them. Right? Okay. So that's the scheme. What might be some problems with this? So just to make sure everyone gets it, we're doing single task RL on different tasks, and then you're distilling it into a single policy with multitask supervised learning. So you're just going to do maximum likelihood. You're going to append in the task vector into your policy and do supervised learning, so no data growth.
Wait, isn't one of the motivation behind those tasks to share data when you're training models?
Yeah, exactly. Yeah, exactly. You're not sharing data. That's a good point. So the objective makes it a little bit better, but it's still going to be a bit of a problem. So they did something that looks a little bit better than not sharing data at all. So the objective they kind of put together was something that looks like this. So it looks a little complicated, but all it's saying is that imagine that you had n different specialists, right? Let's call these specialists. So these are like single task policies, and this is a generalist. Right? So pi naught is going to take in your particular task vector or whatever. And pi I, 1 to n is not. Those are like your specialist problems. And you're going to combine 3 different things. This is the RL objective. This is a supervised learning objective. And this is a maxent objective. So what you're doing here is that you're going to alternate between optimizing pi naught, which is your generalist, and optimizing pi 1 to n, which are your specialists, right? So let's kind of take a look at what each of these updates would look like, right? So if you look at, you can kind of think of this term as like maximizing reward, and this term is like minimizing the divergence between pi I and pi naught, right? So you can kind of think of this as saying you want to maximize the reward while keeping each of the individual policies as close as possible to the generalist, right? So you don't want it to behave super differently from the generalist. And so this is like often called like KL regularization. And this is your max center. Yeah. So 3 terms. And then you're going to like maximize this with respect to pi I, and then maximize this with respect to pi naught. Yeah. So you're just going to alternate between them. So let's look at what each of these objectives would look like. You have a per task reward. You have something that matches pi i's to pi naught. And then you have something that doesn't.
How do you generalize that to an unseen task?
How do you generalize that to an unseen task? So here what we're going to do is you're going to feed in something that is like a task descriptor into your pi naught. So your pi naught is going to be an A given S and some task descriptor. Now, if this task descriptor is just like, you know, a one hot vector, then you're not going to generalize anywhere. But if you, let's say, had like something like a language instruction or a goal image, then the hope is that if you train across enough tasks, you can like stick in something new, and it's going to be like in distribution for things you've seen, and your policy should generalize. So you're not going to rerun RL at test time. You're just going to hope that your policy generalizes because in distribution.
I see, so you kind of omit the movement from your giant.
That's right. That's right.
One of the reasons I can think of like using this is, it's very reminiscent of like RNA maybe, but you can, RNA didn't do this. Like one of the things you can imagine is like you have a quadruped and you train on n different things. And then you train something else to figure out which kind of terrain you're on based on proprioception.
Mhm.
And then the task ID or like the input about what kind of terrain is the task ID.
Yeah.
And that might actually.
That could be part of your generalist policy. Yeah. Okay, so if you optimize the RL objective, right? Or so you optimize with respect to pi I, you can see that each of these terms depends on pi I, right? So the expectation, remember the expectations under pi I, because you're trying to do single task RL, right? So when I say expectations under pi I, you're collecting data under each of your specialists, right? So you're collecting data under each of your specialists. The first term is just doing maximizing reward. The last term is just doing maximizing entropy. And what this term just says, it's kind of like a loss that encourages your RL thing not to diverge too much from like a shared generalist. So if you remember how PPO kind of worked, we didn't want the new policy to go too far from the old policy. It's kind of similar, saying like, don't let the specialists go too far away from the shared generalist, right? And so to answer your question from before, how do you share data? The way you share data is through that like second term. Because it's like pi naught is learned not just on one task, it's across all tasks. And so you're trying to get pi naught to keep pi I kind of easy. It's not the best type of data sharing, but that's how it's shared. So this is kind of maximizing reward, maximizing entropy, and this is saying like specialists should be like close to generalists, right? And then supervised learning is trying to optimize this objective with respect to pi naught, right? And so this term doesn't depend on pi naught. This term doesn't depend on pi naught. The only term that depends on pi naught is this guy, right? And you can see that this objective essentially boils down to supervised learning with data drawn from the specialist. So it's going to be expectation pi I of log or minus log pi naught, given S. Right, so this is, you're going to try and maximize this, right? So this is just, you can kind of think of this as supervised learning on data which is drawn from pi I, right? So optimizing this with like a pi naught is supervised learning. because the expectations under pi I. Optimizing with respect to pi I is RL, right? So you've broken this up into multitask RL, or single task RL and multitask supervised learning. Okay. So in practice, you just like have k different policies that are running. Every once in a while, you collect data from all of them, distill into a shared thing, and then you keep running the policies, collect data, and keep running. That's kind of this divide and conquer procedure. Make sense? Simple. Okay. So does this work? Seems to work pretty well. You can see the line labeled DNC. Our centralized DNC is this divide and conquer distillation type approach, which seems to do a lot better than just this plain old multitask policy. Seems to solve tasks that were pretty hard at the time. So if you see monolithic RL, so RL which tries to do just plain old multitask RL, feeding in your task ID or some descriptor of your task into the input, is like quite poor because of this interference issue. But if you do this divide and conquer thing, you get good asymptotic performance at high efficiency.
How does it compare to specialists?
How does it compare to specialists? Don't know if we have that here, but it's generally faster than specialists and better generalizing to the k+1th problem. So it lets you work on the k+1th thing. That's why it's better than a specialist. Asymptotically, a little bit worse, but generally faster and more generalizable while being a little asymptotic.
What is TRPM supposed to?
Oh, that's just like trust region policy optimization. The RL algorithm we covered in
Yeah, no, single task or?
single task. Sorry, multitask. Multitask with task ID. It's in these cases actually not. It's not multitask per se. It's like multi-initial condition. And it's like the initial condition is inside the state. Good one. Any question? Okay. Okay. So these are some videos from their paper, which I thought were fun. And so you can see that TRPO doesn't do very well, but their divide and conquer approach seems to do pretty well. So here their tasks are different regions of the state space. And all of the issues of multitask RL also show up if your state space is wide enough. And so they're trying to do kind of like what Sid was talking about, things with different heights and so on. Okay. As you were just pointing out, basically a lot of the learning is done independently. You're not sharing that much data. So we want to do better than that, right? So we want to share more data between the tasks than just like this one. Right now, we're just sharing it through this one regularization term, which is not the best. How do we share more information between our tasks? So we can try and do the other approach, which is trying to deal with conflicting gradients, right? And so our issue was that if we had conflicting gradients on G, J, and GI, then like all of the progress that's happening here, you're kind of like undoing with this other task. And so the idea was super simple. It's basically, what if we just try to deconflict the gradients? So you're going to say that if two tasks are conflicting, which means the dot product of their gradients is negative, right? You're just going to try and like project it onto the orthogonal. Okay? And so you're going to say, let me like modify the gradients so that they're no longer conflicting. So you're going to see if two things are not conflicting, right? You can see that you keep the gradients the same, right? The dot product is positive. But if two things are conflicting, you basically kill the part of the gradient that is conflicting. So you like project it onto the normal, right? And so then you get things that are no longer conflicting. And so you're going to try and replace GJ by a projection and GI by a projection, right? So the idea is when you have things that are conflicting, project them to deconflict. So we're going to just take GI, project it onto the normal with GJ, GJ, and project it onto the normal with GI. And so the point here is that you're modifying the gradient, like Rico was saying. You're losing some of the convergence rate, but you're not completely not going in the direction you wanted to go. You're only killing the part of it that is conflicting, right? So you're saying that like this task is gonna be projected. You're going to go into the normal. And now you have like a modified gradient where this thing is no longer conflicting with this guy. Now, what's going to happen is that your descent direction is going to be changed, right? So it's going to get to a better optimum, but it's going to get there slower. So you can show that it kind of like, it's better than multitask RL because it doesn't get stuck in this like conflicting gradient problem. But it is a bit, if you did single task RL, it would be a bit slower than that. So all you really have to do is take your gradient GI and project it. This is just a projection of your gradient onto the unit normal in the direction of GJ, right? So you're going to take GI, you're going to, or the unit normal perpendicular to G, right? And so you're going to like project it on the unit normal perpendicular to GJ. So you're going to kill the part of the gradient that is like directly conflicting with GJ. Right? And so you're going to do this across different tasks. And then you're going to add up your gradient if they're conflicting, and if they're not conflicting, just leave it alone. So we call this gradient surgery, but it's basically just trying to like modify your gradient so they're not conflicting across tasks. And if you try this on simple problems, like this is just a 2-parameter optimization problem. You can see the optimum is somewhere around here. You just try Adam, tends to get stuck. You try Adam with this deconflicting gradient objective, tends to find the optimum. So has nice properties. And if you go back to the multitask RL problem, you can see this. We're calling this thing PC grad. But if you look at PC grad, it's shown in purple or dark purple. It's this line over here. It does a lot better than single task, multitask RL. And it does better, it's more efficient than single task RL because you're sharing information between the tasks with off policy RL. And you tend to do like asymptotically pretty well. Right? So you'll see that eventually this thing will go a little bit above this thing. And so to Michael's question, you'll see a little bit of an asymptotic drop, but it's like much better than plain old multitask RL. Right? So all we did is we said we're gonna take these conflicting gradients, things where the dot product of the gradients was negative, project it onto the normal. And if they're non-conflicting, which means the dot product is positive, you leave it as is. Right? And then that gives you much better multitask RL performance. Right? So if you modify the gradients, you get the dark purple line on top. Seems to do really well for multitask RL. Right? So this is a bit nicer than the distillation method because it allows you to share data more naturally rather than having k different policies. It's better on memory. You're not learning k different models. You're learning one model. You're just like changing the gradients a bit. And yeah, so questions. Go ahead.
So take the projection, so they're conflicting. How do I know which task should I take the projection of and which task?
So in practice, we basically you do it like you just sample a bunch of pairs like randomly between the tasks, and then you like will choose one as the first and one as the second project.
And order doesn't matter.
The order doesn't matter. Yeah. So like you pick them randomly. So sometimes you project A onto B, sometimes you project B onto A.
Like doing that would be like
This one? This one is single task. Yeah. Or yeah, independent. Yeah, single task.
why is it
It like eventually gets to the same optimum, right? So if you look at MT10 and MT50, it like eventually gets to the same optimum. It's just slower. So it's learning one task at a time. So it has no data sharing from the other task. Yeah, so you can go look at the paper for some more proofs and so on. It's like so it's a reasonably easy approach to change any multitask RL problem. But then you can try and apply multitask RL at scale. So this is an example from Google where they did multitask Q learning at scale. They actually didn't end up using PC grad. They used a different approach where they had multiple heads of their Q function. So they had a lot of the Q function shared, and they had like multiple heads coming off the Q function for different. which doesn't allow you to generalize to new tasks as well, but seem to work well at scale. And they apply this across, I forget how many tasks, but they ran it for over a year, just collecting data across different tasks. And they found that like training things multitask generally gives you better asymptotic performance and faster learning than just doing things single task. And then you can also apply it to things with like language conditioning. So this is an example called SayCan. Many of you might have heard about from Google, where they learn a multitask policy with offline RL at the low level, and then sequence things with an LLM planner at the high level. Right. And so each of these are different like task instructions. These are your omega I's. And you have a policy that's conditioned on all of them that you're training with some offline RL type procedure. Okay. So the takeaways here is that multitask RL could solve a contextual meta MDP for zero-shot generalization, should help with generalization to new problems, and because you can do data sharing, it helps with efficiency. Optimization in multitask RL can be challenging because you combine gradient interference with exploration, right? And some solutions include divide and conquer plus distillation, gradient projection, and new things that we have to invent. Okay, questions?
So like my understanding is like the gradients are equal to like each of the types. So if you have like more than one, like how do you fit that? Because in the case that you showed, it was like two gradients.
So you like compute the gradients for, like you'll take a batch from a single task and batch from another task. And normally what your gradient is going to be is like, you have G1, G2, G3, Gn, you like add all of them up. So like your batch will have a bunch of, it'll be composed of data from each of these tasks. You compute the gradient individually, and then you sum it up. And here what we're going to do is we're going to have the same thing, and then you're going to choose pairs of things. Like I was just telling Pranav, basically you'll choose pairs of things and like deconflict those two. And you'll choose another pair of things and deconflict those two. Another pair of things and deconflict those. And so you like do this pairwise deconflicting. That's it.
To that point, so when you deconflict, so let's say you do deconflicting of G1 and G2, and you have also got G2. So when you deconflict G1 and G2, now you have G1, 2. And
It may be conflicting with 3.
yeah, so
Yeah.
now so do you have to like recursively keep doing it until
We-
you get one gradient?
We don't do that.
Okay.
So all the proofs really are in the 2-task case. But the empirical results are in the multitask case.
Like empirically, how do you do it? Do you
You don't do it recursively. You just choose pairs of things, and like you would like deconflict the pairs. Right. So it's like you choose G1, G2, you like pick, you're trying to deconflict, so you like project this guy onto this guy, right? Now you have some G3, G4, you pick those two, and you like deconflict this guy onto this guy. And then if you choose like this one and this one, if that gets chosen again, then you'll have to deconflict it again.
oh, no. Saying is you deconflicted G1 and G2,
Mhm.
which now gives you a new gradient,
Mhm.
like when you sum them up.
Yeah.
So let's call that.
So we don't actually touch the new gradient. You
Okay.
just like are dealing with the individual task gradient.
So it's possible that the combination of G1, G2,
Yeah,
which is let's say
it's
G1,
possible.
2,
Yeah.
could conflict with G3, 4.
So certainly there's a lot left to be desired in terms of the methodology, but it seems to work pretty well.
Is there a larger lesson in that about learning to optimize in general when you're practicing things that lead to conflicting updates? Or is this really specific to
Um,
It seems potentially like it's a much more general optimization.
I guess we applied it to some problems in supervised learning too. I helped a little bit, but the gains were kind of minimal. Honestly, what seems to help the most in large scale multitask supervised learning is just having really large batch sizes.
Yeah.
And so if you can find a way computationally to increase your batch size a lot, I think that tends to like really help with optimization.
That makes sense.
Because you're like dealing with all of the tasks at once, so you don't have this like dithering that you have with smaller batch size.
briefly if there are ever situations where the tasks are so like opposing, I guess, to each other that even if you were to project one onto the other, like you never get above, say, like random performance or like super.
So I guess the tasks, your policy class is taking in your task descriptor. So there always exists a policy that can solve everything, because you're not just saying that you're not just learning an unconditional policy, you're like conditioning it on the task. So even if things are completely separated, your task ID basically would separate your parameters into two different parts and you share nothing. And so that always exists in your policy class. It's just that optimizing to find it is hard. So we didn't find that kind of thing happened, but it can happen. The things are conflicting, and you can still find a policy that is successful at both by just complete separation. Okay.
If you have like a large enough model,
Uh-huh.
you do like you're having conditioning information about like what class we're doing. Can the model sort of like figure out on its own like how to condition like some of its parameters to like dedicate for certain tasks, and then you like sort of avoid this issue when you do.
I think in principle, yes. Right? In principle, you should be able to, because you're feeding in the task conditioning, and so you should be able to separate while still maximizing likelihood or maximizing reward. But in practice, when you're mixing in exploration, I think it becomes hard to do that unless your batch size is big enough. So you see every task all the time. But I guess I would say it's a bit of an open question. But I haven't seen it happen yet. There's like a bunch of work on like these routing networks and modular networks and so on, which try to you know what I'm talking about, right? Like they have like different modules and you like automatically learn the route between them. But I haven't seen them use that much in practice besides this mixture of experts type model that LLMs often use.
Similar like where there's many tasks that LLM needs to solve and like.
Yeah, they kind of like separate it into the mixture of experts and have a gating model that chooses which of them you should use. And like a modular network is just a multi-layer mixture of experts. You can think of them as a mixture of experts of multiple layers and you're finding a path through them. I would say before a year and a half ago, they weren't used that much. And I think they found more use in LLMs. So I think we should revisit them, but I wouldn't say there's anything super conclusive about those models in RL. Okay, questions? Anything else before we move to meta RL? Good. All right. So meta RL is very similar to multitask RL, but multitask RL is all about zero-shot generalization, right? So you're saying, I'm going to feed in a new task. I'm going to say, pick up the mug, and you're going to have to pick up the mug zero-shot, right? And the whole goal here is generalizing to a new task without any more training at test time, right? So you're trying to do multitask RL, you learn a policy. Policy is going to take in a state, task descriptor, perform well at the new task zero-shot. Right? If your new task is in distribution, the hope is that you will generalize. If it's out of distribution, you may not generalize, but it may not always be enough. Right? So when is it not enough? Like what are settings where you might want to do more than this? Like essentially what I'm trying to ask is, what are some settings where you might want to do more than zero-shot generalization? Other examples in your workflows that come to mind?
Requires combining two tasks.
Yeah, combining two tasks, some composition.
Something that wants to behave differently.
Yeah, where you want to behave differently. Yeah, absolutely. Or where you may have a task that's out of distribution. Right? So what meta reinforcement learning tries to do is it tries to ask this question of how do I go beyond zero-shot generalization? So you're trying to go from zero-shot to few-shot generalization, right? So an example Sid brought up a little while ago is this thing called RMA, right? And so what RMA does is it tries to do, it tries to say, I'm going to it's trying to do locomotion. You're trying to have a robot adapt to new terrains, but you don't know the parameters of the terrain beforehand. So you're just like walking on ice. I don't know that it's ice. And you're trying to quickly adapt to your new terrain. Right? So Meta learning or few-shot learning is about quickly changing your policy to a new setting. It could be a new task, that's OOD. It could be a new way of doing things. It could be something with this partial observability, right? So you can't see what the terrain parameters are, right? And you have to figure that out through experience. And so in all of these settings, we're trying to think about, so either when your policy is not good enough and you have to fine tune it, or where you have partial observability and you have to figure out what your terrain parameters are through experience. You want to do things that are not zero shot. Like how do I walk on ice if I can't tell that it's ice? But you want to do things that are few shot, right? And so while multitask RL says agent dropped in world works zero shot, Meta RL tries to say, how do we learn very, very quickly with the smallest amount of experience, right? So you're going to have an agent which is deployed in the world, get some experience, it changes, get some experience, it changes, and so on, right? But the goal of Meta RL is to learn as quickly as possible. So rather than multitask RL, which is trying to say maximize zero-shot performance, the goal of Meta RL is to learn as quickly as possible. So maximize the area under the curve, essentially, right? So it's saying that if I'm in a new task, I really want to learn as quickly as possible, right? And so there's this notion of something called regret, which is the difference between the sum of differences between your current policy and the performance of an optimal policy in hindsight. If you sum this up from 1 to n, right, that's something called regret. So regret is saying that how much worse were you than an optimal policy chosen in hindsight. And the goal of meta reinforcement learning is to minimize regret. That's you're trying to maximize the area under the curve, minimize regret, learn as fast as possible. All of those mean the same thing. Yep. Okay, so we're going to try and design. Here we were talking about optimization as the main problem. Now we have to design a set of algorithms that can learn quickly, right? And so multitask RL is about learning a single policy that can work in new settings. Zero shot Meta RL is about doing a learning algorithm that can quickly adapt to new settings, right? And so Meta RL is about learning to learn. And so rather than trying to learn just a policy, you're trying to learn an adaptation procedure so that in a new problem you can adapt quickly, right? So Meta RL tries to learn a good K-shot policy by learning how to learn. Right? How many of you have heard of meta learning before? Yes. Okay, so meta learning is kind of like there's normally when you have learning, you try to take in data, put it through a known learning procedure of policy RL, SAC, policy gradient, something like that. Like out comes a good set of parameters, right? But it's slow. And so what Meta RL tries to do is it says there's some regularity in those problems, right? There's all of those are sports with some regularity. You're going to try and leverage the regularity of your problem to learn a procedure that is much faster than SAC or much faster than policy gradient, right? So at any point of time in a new setting, you could apply policy gradient, you could apply SAC, you could apply some RL algorithm to learn. But what a meta RL algorithm says is that those are inefficient because they're overly general. Instead, I'm going to learn, so let's say SAC was going like this. Here, I'm going to try and learn a procedure that is way, way, way faster, right? And there's no free lunch. It's not going to happen magically. What you're going to have is that there's some regularity in these sets of tasks. And this task has to be somewhat near these tasks for this to apply. It's not going to work on everything. Basically, if I do meta learning on every problem, then I get back to nothing, right? So this is no free lunch theory. But the point of meta learning is if I know a set of related problems, I can train on them and I can learn a fast learning procedure that can quickly adapt to new problems. That makes sense as a premise, right? And so remember, the goal of Meta RL is not to learn just a policy, it's to learn an update rule that can update your policy in new settings. Okay, so the formalism we're going to use is you have a bunch of training data. I'm going to call it meta training, a bunch of training problems. You're going to try and learn a policy and an update rule such that when you go to a new task in meta testing, you can quickly adapt to those tasks, right? So think of it this way. There's like a bunch of different tasks, right? Each of these are tasks. This is what you call meta train. And now you want to adapt to a new task, which is what you have at meta test. You're going to learn an update rule. From this, you're going to learn some update rule, which can take in, update rule is going to take in theta, output theta prime. Yeah. And so your update rule at test time is going to take in your initial theta and quickly output theta prime, prime, so on till you get to like optimal quickly. Right? So what you're going to learn is this like update rule rather than just a policy. Yeah. Okay. So this seems cool. How do you do it? Right, so the goal here is that given some distribution over tasks, you want to learn an update function f theta so that you can learn new tasks run from p tau. P tau is your distribution of tasks quickly. Right? How are we going to do it? Thoughts?
Do we have a description of the task?
You have a description of the task. So let's write out the formalism first, and then that'll make it clear. Right. So standard reinforcement learning is going to say we want to maximize the sum of rewards for a single task. And so you're given a reward, you want to learn a phi theta. In meta-RL, we're going to try and learn an update function f theta. Right. So let's say our parameters of our policy were phi I. F theta is going to take in phi naught and give me phi 1. And it's going to take in phi 1 and give me phi 2. Right? And so my updates and my policy parameters are done by f theta. And what I'm going to try and do, so I'm going to be told my task is going to be coming through my reward function. So my reward function is going to tell me, let's assume that the dynamics are the same for now and just the rewards change between tasks. So to answer this question, we get the rewards from, we get the task description from the rewards, right? And we are trying to figure out the parameters of a learning rule that can take in a previous policy parameter and give me a new policy parameter. Right? And so the goal of meta-RL, so if you look at standard RL, the goal is to learn the parameters of a policy. The goal of meta-RL is to learn the parameters of your update rule, not the parameters of your policy. Yeah. And so remember, the update rule takes in the policy parameters. This is your policy parameters. These are your update rule parameters. Okay, make sense? So you're trying to leverage experience across 8 different problems such that you learn the update rule, which leads to the fastest learning on a new task drawn from that distribution of tasks. Okay, so that's the problem setting. This is your policy parameters per task. These are the parameters of your update rule. You're trying to learn theta. The goal here is to encourage a quick update. So one thing you want to notice here is that I think I had a little typo here, but basically your inner sum is, let's say you like updated your policy parameters with f theta. Let's say you went from phi naught to phi 1 to phi 2 to phi 3. You're going to like have your inner loop summing over, let's say, I from 1 to k. Right? So you're trying to say, like what this objective is going to try and do is going to maximize the expected sum of rewards across multiple iterates of phi. And that is going to be maximized when phi gets to the optimal policy as soon as possible. Right? And so the important thing in this objective is that, which I seem to have forgotten, is that you like have to sum up over I from 1 to k. And this thing is going to consider basically not just phi naught, not just how good phi naught is, but it's going to say phi naught goes to phi 1, goes to phi 2, goes to phi 3. And you want to sum up the rewards of each of these policies, right? And that whole objective is maximized if I get to phi star ASAP and stay there, right? And so the best update rule is something that maximizes the sum of rewards across multiple of these. And that's going to try and optimize for regret. Does that make sense? Yeah.
So every item is different.
Yeah, so the way this is going to work is that imagine that you like, let's say this was task 1. Yeah. So you're going to start from some, let's call it phi naught. And for this task, you're going to use your f theta using some task specific information like your reward to update this to phi 1, phi 2, phi 3. Let's give this a superscript of 1. Yeah. And then you'll have, for another task, you'll repeat the same adaptation procedure, but you'll have a difference. You'll start from the same phi naught, but you'll update to phi naught 2 or phi 1 2, phi 2 2, phi 3 2. So you're going to use the same update rule, but it's going to take in different rewards, and each of the phis will be updated differently per task, right? So you can think of this as like you're going to start from some initialization, but one task will go this way, another task may go this way, right? But in all of those settings, you're applying f theta as your update rule, right? So the phis are the phis are different for different tasks, right? So you can kind of think of this as this is kind of like an inner loop where you're saying you're starting from some phi naught, updating it using f theta differently per task. And the outer loop is saying you want to make that f theta good across all the tasks. Does that make sense? Okay, let's try and draw it out a little more. So we are gonna let's think of policy parameters as phis, okay? So, and let's say all at every task, let's draw let's call this task 1, okay? You're going to start from some policy parameters phi naught. Now, your update rule is going to say, I'm going to take in phi naught. I'm going to take in some rewards that I get by running phi naught, and I'm going to update phi naught to phi 1 1. And I'm going to apply the same update rule again. It's going to give me phi 2 1. Give me phi 3 1. Right? So for this task, I like started from some phi naught initialization. I applied f theta, and it gave me like some updated parameters. Right? So after k steps, let's say I reached phi k 1. Now, let's say I had a different task, right? Now you're going to start from, let's say you start from the same parameters phi naught. But because my update rule is going to take in phi naught and rewards from that particular task, these rewards are not the same as these rewards, not the same. Which means that this update is going to send me to phi 1 2, phi 2 2, all the way to phi k 2, right? And this is not equal to this, right? So, but the same update rule is used across both settings, right? But exactly. It's like the update that can learn different tasks, and the difference is that your R's are going to be different, right? And so the updates are going to be different because the thing that's identifying the task and the progress is different. And so you can kind of think of it as like, that's why I drew that line earlier, is like you're starting from phi naught. The adaptation in one task would take you this way. The adaptation in another task might take you this way. An adaptation in another task might take you this way. Right? And you're trying, and each of these adaptation rules are determined by some f theta update. But they're the same update. They're just like different rewards per different task. So this is R1, R2, R3. Right? You're trying to find the same update rule that works across all of the tasks. Right? So the reason is when you have a new task, you want to be able to apply the same update rule. Okay. Questions, thoughts, concerns? It's a little confusing. Yeah.
How is the trajectory in your like pattern?
Yeah. So no, sorry, no. Tau is your task. So tau is like this is task, sorry. So these are like, this is an expectation over like tasks. And this is like data drawn from your task. So this would be like S, A, S prime, and reward, which is task specific. Yeah. So the important part of this objective is that it's like in expectation over tasks, you want like the reward for that task to be as high as possible, as quickly as possible, right? And so your update rule inside this like summation I, your update rule is updating phi I every time. And you want that to get to as high as possible in expectation over all the tasks, right? So each of the tasks may have their own parameters, but they all use the same update rule. And you're trying to find an update rule that works well in expectation over all the tasks.
So could you say you're learning something that you're using in lieu of Atom or
Yes,
SGD?
exactly.
You're learning something that's more specific.
That's right. So since there's no free lunch, it's like, it's not going to be better on all problems, but it is going to be better on the set of problems that you consider here. Interesting. Now, it's more like something in lieu of policy gradient here because we're doing RL, but you can apply this just as easily to like supervised learning. Like this doesn't have to be an R. This is an RL objective right now. It doesn't have to be. It could be like a supervised learning objective. So the point here is that you may have like phi i's, like this should really be like phi I tau to your one's point, right? Like, but phi i's can be different, but f thetas are the same. Okay. Kind of makes sense? Yes? Okay, so we'll go into more detail. But some intuition here. This is a paper called RL Square from a few years ago, or like 10 years ago, where they're trying to like solve new mazes. So the goal is to get to like this region, right? And so what they're trying to do is learn an exploration strategy, such that you like learn how to explore mazes, and once you find reward, you very quickly hone into like going back to that place repeatedly, right? And so what they learn to do is they learn to like, you can see that it's learning like somewhat coherent searching behavior. So it's like learning to search, and as soon as you start seeing reward, you just like hone in on that and keep repeating, right? And so the idea behind these kinds of methods is that it's learning a quick update rule, and the quick update rule has to learn how to search. Like basically, the nice part about if you did meta learning perfectly, you would learn how to explore, because the way to do quick adaptation is you have to explore, right? And so the goal here is you want to leverage some regularity. You explore for a while, you learn how to explore, and then you can quickly adapt to new problems, right? And rather than just maximizing reward, you're trying to minimize regret. So you're saying you can do something that is a little suboptimal first to gather information to then be optimal. And so for those of you who are interested in POMDPs, it's like a good way to solve POMDPs. And so you're trying to say, you're trying to like identify the problem first, and you might be suboptimal. So it's like if you're searching for treasure, you might first learn to go find the map, and then you might learn to solve your task, right? So what meta RL should learn is a strategy that first finds the map and then solves it. Okay, so what is the general structure of a meta RL algorithm, right? So as I was saying earlier, there's an inner loop and there's an outer loop, right? So the inner loop, let's say, is something that, your inner loop is something that tries to update from phi naught 1 to phi 1, 1 to phi 2, 1, and so on, right? Or like more generally, phi naught tau to phi 1 tau to phi 2 tau. So it's like learning, and it's running an update using f theta as your update rule. And your outer loop is trying to evaluate in expectation across all the tasks, how good is your update rule, right? So the inner loop is updating your policy parameters, and you're seeing how good those policy parameters are. And your outer loop is trying to say, I'm going to run this update rule across k different problems. I'm going to see how good my update rule is, right? And so the general structure of a meta RL algorithm is that you're going to try and instantiate the outer loop in some way. You're going to instantiate the inner loop in some way. And different meta RL algorithms are just different choices of outer and inner loop. So generally, you start by sampling a batch of tasks from p tau. Then you collect some data before an update, right? So you start from phi naught, you collect some data. Then you compute an update according to f theta, right? And then let's say you started from phi naught, you collected some data. Then you ran this through f theta. This gave you phi naught 1, or sorry, let's call this phi 1 for task 1. And let's say it gave me phi 1 for task 2 and gave me phi 1 for task 3, right? So I started from phi naught and I ran my update rule. It gave me k different updates for k different tasks, right? Then you're going to try and evaluate how good those updates were. So once you've like updated it to each of these, you'll collect more data from each of these and use that to evaluate how good f theta was. So you can think of this as initial data is used to perform the update. After you perform the update, you want to collect data to see how good each of these were. You're going to use that to update f theta. And so the general scheme is sample a batch of tasks, collect data from phi naught or your data pre-update, perform your update according to F theta, then collect data post-update to see how good your updates were, right? And then you use that to update F theta, right? And so you're going to do this in batch over many different tasks, but remember, you're going to share the same F theta across all. Okay. This makes sense overall? There's an inner loop, there's the outer loop. You can kind of think of the inner loop as like modifying your policy parameters, and your outer loop as modifying your update rule, right? And so the outer loop will modify the update rule. Every modification of the update rule will affect the inner loop because the inner loop is just running at theta. Okay, so there's lots of different solution techniques. There's different choices of the inner loop and the outer loop, right? So the choice of F theta, the form of F theta and the different types of algorithms will lead to different meta-RL methods, right? So if you instantiate F theta as an RNN or like a transformer or something memory-based, you get this like class of methods RL square or in-context learning, is often what you'll hear. If you instantiate F theta as a posterior inference type of method, you'll get latent variable meta learning. If you instantiate F theta as gradient descent, you get a class of methods called MAML, model agnostic meta learning. Right? And so that's kind of like different choices of inner loop will lead to different algorithms. And in the outer loop, you can have different algorithms. You can have policy gradient, you can have off policy RL, you can have model-based RL, and each of those will lead to different algorithms. Right? So we'll explore a few of them, but whenever you're trying to design a new meta-RL algorithm, think of how you want to instantiate your inner loop, think of how you want to instantiate your outer loop, right? And that'll give you a new algorithm. You can write infinite papers. Okay, so let's try to think about the first and simplest way to do this, which is memory-based meta-RL. It's like, I guess it's so dumb and obvious that it's almost treated as de facto. Like people already do this, but it wasn't that obvious when it came out. Right? So the idea here is that your update function is the forward pass of an RNN. And your policy at any point are the activations of your RNN. Right? So if you think of an RNN, you can kind of think of it as like you're like updating your hidden state over time, right? So you're like getting some inputs, but you're updating your hidden state over time. So the activations of your RNN at any point of time are your policy, and your like one-step RNN update is kind of like your learning tool, right? And so what memory-based meta-RL does is it says, let's learn an RNN that takes in your past states, actions, and rewards into your policy as history, right? And let's try and produce actions from there. So it's like, let me learn a history condition policy. I'm going to learn a history condition policy that takes in not, as opposed to everything we've been doing, which is Markovian, it's going to take in like a history of like, states in the past, actions in the past, and rewards in the past, right? So a few differences. One of them is that you're conditioning on history. And the second is that you're conditioning on reward. Like we've never conditioned on reward before, right? So you're going to run RL, but you're going to learn a policy that takes in state, action, and rewards in the past. Why do you need to do that? Is because how do you do an update if you don't know what worked and didn't work in the past, right? And so your history takes in state, action, reward across different, and you're going to run this policy across different episodes. Like for instance, you're going to try going the maze this way, you're going to try going the maze this way, you're going to try going to the maze this way. Normally in an RNN, you're going to reset the hidden state whenever you run inference. Here, you're not going to reset the hidden state between episodes, which means that you're going to run your RNN here, and then you're going to carry over this hidden state even if your agent restarts from here. So it's kind of like you remember what you saw so that you can use that to inform your update rule the next time. You're going to remember what you saw to inform your update rule the next time, right? And so essentially what you're going to do is you're going to learn a history conditioned RNN, right? But you're just going to make two changes. You're going to condition on reward. You're going to maintain the hidden state across episodes, and you're going to maximize the sum of rewards across episodes, right? And so you can use any RL algorithm. You can use PPO, off policy RL, whatever you want. Well, PPO is easier than others, but you're just going to make sure that it's conditioned on past reward, right? So essentially if you like optimize the objective fully, let's see, I have this on the next slide. If you optimize this objective fully, the way it's going to work is you're going to sample a batch of tasks. Then you're going to run your RNN forward, right? You're just going to run inference with your RNN. And you can kind of think of it as like your RNN has, you go back to this figure here, your RNN has a hidden state, right? Your hidden state is like kind of like your policy parameters at any point of time. And your RNN internal update is kind of like updating your policy. And so it's taking in states, actions, rewards, and it's updating your policy. So like what does an RL update do? It takes in states, actions, rewards, and it updates your policy. All this is doing is it's saying all of that is going to be embedded into one forward pass of an RNN. Yeah.
Wait, so is this RNN referring to like we make the policy an RNN?
Yeah, the policy is an RNN. So the policy, the trick is that the policy and the update rule are just like merged into the RNN. So basically the state of the RNN at any point of time is the policy. Like as in, I run my RNN right now, it's going to give me the policy. And then I'm going to take in what I saw, feed it back into the RNN. And then like I run the RNN forward, and that's like an update rule. And so it's like the RNN is both the policy and the update rule.
So every hidden state in the RNN is a policy.
That's right.
All right.
Every hidden state in your RNN is a policy, and every forward step of your RNN is the update. Right. So it's kind of like your RNN contains both the policy and the update. Right. So this is kind of what you do in like in context learning too. It's kind of you have a big transformer, and your big transformer takes in some history of states, actions, rewards, or in LLM land, it's going to take in like examples of success, right? And then it's going to like, because it's running a forward pass of memory, it's going to like perform an update internally. And as you get more experience, you feed that continuously into context. And so all you're going to do here at training time, you're just going to run PPO. You're just going to do PPO with recurrent policy. So you're going to make a few changes. You're going to do PPO with the recurrent policy, feed in R or feed in SAR, and don't reset hidden state over episodes. Right? That's all. So to go from RL to meta RL, you just need to make those three changes. Right? Does that make sense overall? Got a question, Pranav? So the procedure looks the following. You collect a batch of tasks. For each of those tasks, you're going to run your RNN policy. Remember, your RNN policy is going to take in state, action, and reward. You're then going to try and optimize your RNN policy to maximize the sum of rewards in expectation over tasks with policy gradient. So going to factor up through time with policy gradient, and you're going to repeat, right? So it's a little bit counterintuitive, but basically your RNN policy is optimum. Like your RNN policy is universal in a way, right? So you can, if you have a big enough neural net, you can compute any computation here. It's just something that takes in SAR and tells you what the next thing should be, right? And so the hope here is that because it's universal, the optimum to this objective would be that this becomes the most efficient RL procedure that you can possibly have, right? In this set of problems. And so you just do a procedure like this. At test time, you just need to run your RNN forward. There's no optimization at test time. You're just running your RNN forward. You're taking in states, actions, rewards in the past. You're getting an action to take in the future. Feed that back in, feed that back in, feed that back in, right? So there's no optimization at test time. You're just running your RNN forward because your update rule is just the forward pass of the RNN. You can replace this with a transformer or whatever else you want, but it's kind of the same idea. Does it make sense? It's a little bit counterintuitive, but it's like the easiest way I find to think about it is that your policy is your activations, and your forward pass of your RNN is your update rule. And this if you train it with RL, it is incentivized to try and maximize the reward as quickly as possible. Right? Because you're saying I'm going to sum up the rewards across multiple different episodes. I want to get as high a reward as possible across episodes. So I'm going to try and like get there as soon as I can. Okay. So that's memory-based meta RL. Questions?
How does that scale?
Good question. it's hard to scale because of this, it has this like circular problem. And so the difficult part of meta-RL is that you kind of want to learn how to explore, but to learn how to explore, you have to know how to explore. And so what makes memory-based meta-RL hard to scale is this like chicken and egg problem with exploration. Like imagine that you were in this maze setting, right, that we had earlier. Like I have to like, unless my exploration strategy is good enough to know how to explore, it's hard to optimize the RL objective well enough. And so what makes memory-based meta-RL hard to scale is just this chicken and egg exploration problem. So what has seemed to work is if you take enough tasks. So DeepMind has a nice paper on curriculum learning, where they have like thousands of tasks in an open-ended world, and then some tasks can help other tasks explore. But if you do it in small scale, it's hard to deal with this exploration. The other issue with memory-based meta-RL is that you don't run any optimization at test time, you just run your RNN forward. And so if your RNN is not getting better, it just never gets better. So like you keep running your RNN, it might never get better. Whereas some of the other procedures will like try to optimize like objectives with gradients, and those will continue to get better. And so here you don't have guarantees of getting better. So like, to your question, it's easy to implement. It's arbitrarily flexible, generally stable, but it's not guaranteed to improve. So you'll often see that like RL square will get stuck. It'll learn quickly, but get stuck. Whereas other procedures will continue to converge and get better. And it doesn't do very well out of distribution. So unless you train it on a huge number of tasks, it's hard to get good performance. And so some examples of this kind of working are these maze examples, which are kind of summarized here. So you can see that in the first, it doesn't know that it has to get here. So it like starts from here, explores all around, finds the reward. The second episode, it just goes straight to the goal because it has memory of what it did from the first time. Yep.
Regarding like improving during test time, we make like the update like the data hyperparameters of the gradient descent of the
Yeah, that's what the next method does. Yeah, it's a good idea. So the main point of memory-based meta-RL is just run an RNN, add in rewards as input, and optimize it without resetting the hidden state. That's it. The pros and cons are simple, just doesn't work that well out of distribution. A slight update is that this in-context learning stuff seems to work well when you pre-train on like web scale LLM type data. And so all of these insights are at the like small scale. I think the behavior is different at the massive scale, and I don't think we fully understand it. Interesting area of work. Okay, so to Rico's point, the second idea is what if we just made the inner loop gradient descent, right? And so what if we just said, what if we say F theta is a convergent update rule? What if it's gradient descent? Yeah, so the idea behind the second type of update is to say that I don't want to force F theta to be an RNN like I did earlier. I'm going to make F theta gradient descent. So there's a method called MAML that came out 2017 or so. And what MAML does is it says that my update rule is going to be gradient descent. And so F theta, so if you think about, I think my notation's a little wonky here, but let's think of this as like, let's call this like phi I plus 1 is phi I plus, so it's phi I, right? So this is just like SGD. And so you're saying that in your inner loop, you're going to perform SGD, and you're going to evaluate how good SGD is in your outer loop, right? So you're going to say, I want to force F theta to be SGD. And then I'm going to evaluate after one gradient step or a few gradient steps, how good my updated policies were. Okay? And so the question is, if I did SGD in my inner loop, there's no parameters, right? Like you could do some hyperparameters like Rico was talking about, but what would you learn? Like what are the parameters of your meta update? Like it's just SGD. Right? You can learn alpha if you want, but like that's about it. So my question for you is, If my inner loop was just SGD, let me write this up cleanly so that you don't have to look at this. It is phi I plus 1 is phi I plus alpha grad phi I, expectation pi phi I, sum of rewards, right? So just forget about this. This is cleaner. This is my inner loop, right? What would I learn? There's nothing to learn.
If you learn to scale the different dimensions of your gradient.
You could learn to scale the different dimensions of your gradient. Yeah, so you could have like a preconditioning matrix that you could learn. You could learn the alpha. You could learn something like Rico was getting at, like learn the parameters of an momentum time update rule. But what Chelsea and co found to be a good thing to learn here is to learn the policy initialization that is most amenable to gradient descent, right? So they're trying to say, normally we have been ignoring this initialization, right? So what MAML does is it tries to find the initialization which is most amenable to gradient descent, right? So it's trying to say, if you're learning the update rule with SGD, what you can control is your initialization, right? And so this figure kind of tells you what it is. It's saying that let me find the theta such that if I ran gradient descent on different tasks, I get as close as possible to optimal for each of those tasks. So you try to find the initialization that's most gradient descentable. And so essentially you're trying to find the initialization theta such that when you run gradient descent on it, the post-update phi I is as good as possible across all of the tasks, right? And so the nice thing about gradient descent is you can take gradients to gradient descent. It's just you take the second derivative, right? So this is differentiable, which means that you can optimize this whole thing with just SGD, right? So you just like, you kind of think of this as like you have to just backprop through this with chain rule. And so the nice part about MAML is that it's all differentiable, and you're trying to find the initialization that is most fine-tunable, right? And so the pseudocode here is that you sample a batch of tasks, you collect data pre-update from the same policy parameters by data, always the same parameters. And for different tasks, you perform different updates with gradient descent. But remember that the rewards are different, right? So the rewards are different here. So this is the same, but these are different, which means that these will be different, right? So you start from a theta, and then you'll get like k different phi 1, phi 2, phi 3, something like that, right? And then you try to see how good these are in expectation. And you backprop into finding the best possible theta. And so you're going to compute the update, you're going to sample data from phi I post update, and then you're going to backprop through the whole thing to update your thetas. And so if you work it out, you only need a second derivative. It's not that bad. But the point here is that you like treat your inner loop as gradient descent and you backprop through gradient descent. Right? And so what you're going to learn is an initialization. Right? So the update looks something like this. You're going to try and find the best theta such that when you do gradient descent for one, you could do a few steps on that. Then you get to a phi I, which is as good as possible. You backprop through it. And at test time, what you're going to do is you're going to just run gradient descent. Gradient descent. You're going to start from your theta, just keep on running gradient descent, right? But because you've pre-trained it to be fine-tunable, it's going to be a lot more efficient. So here's some empirical results. So you can see that MAML is shown in green and RL is shown in blue. So you can see that it tends to learn pretty quickly just with plain old gradient descent. And so the thing shown on the top is that's the initialization at 0 gradient steps. So you just sampled from your prior, and then you took one gradient step, just one, and that it learned to walk, but it would never happen if you were just starting from scratch. And so the nice part about it is that it's consistent and it ensures that you keep getting better. You only need to learn an initialization and maybe some scaling parameters. The con is that you need a second order gradient. You have to backprop through gradient descent. And you potentially have a less expressive update because you're only thing you're tweaking is an initialization. Cool. I think we're out of time, but we'll see you guys on Wednesday. Simon's going to give a guest lecture. It's going to be fun. I'll see you there. It'll be here. Thanks.
What app are you using to do your ink during the